Hi students, welcome to My Teacher channel. In the previous sessions of Real Numbers chapter, we have discussed Euclid's division lemma. Let us recap. We know that for any given positive integers a and b, there exists a unique pair of integers q and r satisfying a is equal to bq plus r, where 0 is less than or equal to r less than b. By Euclid's division lemma, a is equal to bq plus r. In this, suppose if r becomes 0, then the equation becomes a is equal to bq. Then, can you tell what must be the relation between A and B? Yes, we can say that A is divisible by B, or B is a factor of A. Now, this concept leads to the fundamental theorem. So, theorem 1.2, the fundamental theorem of arithmetic is like this. Every composite number can be expressed as the product of primes, and this factorization is unique apart from the order in which the prime factors occur. What does it mean? We know the numbers are basically divided into primes and composites. What is a prime number? Yes, a number which has got only two factors, that is 1 and itself. Then what is composite number? A number which has got more than two factors is called a composite number. And now what here it is saying, what the theorem is saying is that the composite number can be factorized or expressed as the product of primes. Is it so? Let us check. Let us take one composite number and try to express it as the product of primes. For example, 210 is a composite number, isn't it? Yes, it has got more than two factors. Now let us check whether this composite number 210 can be expressed or factorized as the product of prime numbers or not. Let us check here. See, 210. Since it is an even number, it is divisible by 2. So 2 is a prime factor. Let me take here 2 ones are 2 and 1 doesn't go. 2 zeros are 0. Now this becomes 10. 2 fives are 10. Now 1 plus 0 plus 5, that means 6. 6 is divisible by 3. So let me check with 3. Yes. 3 threes are 9. Out of 10, 9 gone. 1 left. 1 5 15. 3 fives. And now 35. 35 can be expressed as 5 sevens are 35. Okay. Now see here. 210 is expressed as the product of prime numbers. 2, 3, 5 and 7 are prime numbers. So 2 into 3 into 5 into 7. Is it so? Let's check. 2 threes are 6. 6 fives are 30. 30 into 7 is nothing but 210. So 210, a composite number, is expressed as the product of prime numbers. So the first sentence is proved. Every composite number can be expressed or factorized as a product of primes. Yes, it is true. Then what is saying? This factorization is unique apart from the order in which the prime factors occur. Is it so? Let's check. Suppose if the prime numbers order is changed, say 210 factorized as, see here, let's see, 5 fours are 20, 1 left, 1 and 0, 10, 5 2s are. Next, 2 2s are 4, 2 1s are 2. Great. 7 3s are 21. Let's see here. 210 is expressed as the product of 5, 2, 7 and 3. 5 2s are 10, 10 7s are 70. 70 into 3 is nothing but 210. Now let's see, compare these two. The prime numbers 2, 3, 5 and 7. Here also the same prime numbers are there, 2, 3, 5 and 7. Just the order is different. Even then the product is same. Means the same composite number we are getting. So irrespective of the order in which the primes are occurring, the product is same. Right? So clearly we can understand that every composite number can be expressed or factorized as the product of primes, where this factorization is unique apart from the order in which the factors, the prime factors occur. So from this theorem we understood that every composite number can be expressed as the product of prime numbers. Okay. Now, based on this concept, we got a question in exercise 1.2 of real numbers, and the question is like this. Express each of the following numbers as a product of prime factors. Okay, so here we got 5 numbers and we have to express them as product of prime factors. Let us start with the first one. So the first one is 140. 140. Since it is an even number, 2 is a factor, the first prime number. 2 7s are 14, alright, and 2 zeros are 0. Great. Into table, 2 3s are 6, 1 left, 10. 2 5s are 10. Now 35 doesn't go into table. The next prime number is 3. 35 doesn't come in 3 table also. The next prime number is 5. Yes, since the last digit is 5, it is divisible by 5. So 5 7s are. Since 7 is also a prime number, we'll stop the factorization there. Therefore, 140 can be expressed as 2 into 2, which is nothing but 2 square into 5 into 7. Okay. Similarly, let's do the second one. The second one is 156. Let us do the prime factorization for this. 156. Alright. 2 7s are 14. 1 and 16. 6 is 16. 2 8s are 16. Again in 2 tables. 2 3s are 6. 18. 2 9s are 18. Next. 3 and 9. 3 plus 9 is 12 and 12 is divisible by 3. So 39 is divisible by 3. 3 1s are 3 and 3 3s are 9. And 13 is also a prime number. We'll stop the factorization and we can write as 156 is equal to 2 into 2 is 2 square into 3 into 13. Great. Now we'll go for the third one. And the third one is 3825. 3825. Okay. Now let's see here. 3825. Since the last digit is 5, it is divisible by 5. 5 7s are 35. 38 is there. 35. So what's the difference? 3. 3 to 32. 5 6 are 30. 2 left. 2 5 25. 5 5s are 25. Great. Again 5 is there. So divisible by 5. 5 1s are 5. 7 is there. 2 carries forward. 2 and 6 26. 5 5s are 25. 1 left. 15. 5 3s are 15. 153. Let's see here. 1 plus 5, 6. 6 plus 3, 9. So the sum of all the digits is 9. That means it is divisible by 3. Automatically 153 is also divisible. So let me try with 3. 3 5s are 15, 3 1s are 3. Again, 5 plus 1 is 6. So it goes in 3 table. 3 1s are 3, 2 left, 2 1 21, 3 7s are. So 17 is a prime number. Let's stop here, and therefore 3825 can be expressed as. So let's take the smallest prime number first and then let's increase the order. So 3 into 3 is 3 square into 5 into 5, 5 square into 17. Okay, now we'll go for the fourth one. Fourth one is 5005. So we'll do the prime factorization for this. 5005. So it goes in 5 table. 5 1s are 5, 0, 0, 5 1s are 5. It goes in 7. Let's try with 7. 7 1s are 7, 3 left, 30. 7 4s are 28, 2 left, 21. 7 3s are 21. Next, 143 will go in 11 table. 11 1s are 11, 3 left, 3 and 3 33, 11 3s are 33. So 13 is a prime number. We'll stop the factorization and we can write 5005 as the product of 5 into 7 into 11 into 13. Next, the last one is 7429. Children, it is for you. Try it out. Try to find or try to express this number as the product of prime factors. Students, we have already seen how to find HCF, highest common factor, and LCM, lowest common multiple of two positive given integers by using the prime factorization method in our previous classes without actually realizing it. Now, in this class, let us try to understand how to find the highest common factor, HCF, and LCM, lowest common multiple of two positive integers by using prime factorization method. We'll start with one question. Find the HCF and LCM of 12 and 18 by the prime factorization method. Here the given positive integers are 12 and 18, and we have to use prime factorization method to find HCF and LCM. So we'll start like this. Given integers 12 and 18. Now, first, let us try to find the prime factors for 12 and 18. First, let me start with 12. See here. 12 can be expressed as 2 6 and then 2 3s. 12 is written as 2 into 2 is nothing but 2 square into 3. And only one 3 is there, then the index becomes 1. So 2 square into 3 power 1 is 12. Similarly, let us find the prime factors of 18. See here. 2 9s are 18 and then 3 3s are 9. So 18 can be written as 2 means 2 power 1 into 3 into 3, that is 3 square. Okay, HCF of 12 and 18 is, so the HCF of given integers is the product of smallest powers of each common prime factors of the numbers. See here, the common prime factors 2 and 2 are common, 3 and 3 are common, and now we need to find the product of lowest powers of each common prime factor. So common prime factors 2 square and 2 power 1, and the lowest power is 2 power 1, isn't it? So let me take 2 power 1 into here 3 power 1 and 3 square. These are also common, and the lowest power is 3 power 1, and this product gives the HCF. So that is nothing but 2 power 1 is 2, 3 power 1 is 3, 2 3s are 6, 6 is HCF. This symbol is to find HCF. Now let us find the LCM of given numbers. Then what is the LCM? LCM is the product of greatest power of each prime factor of the given numbers. Now we have to see the greatest power opposite to the first one. So among 2 square and 2 power 1, the greatest power is 2 square. And among 3 power 1 and 3 square, the greatest power is 3 square. So 2 square is 4 into 3 square is 9. 4 9s are 36, and that is the LCM of the given numbers 12 and 18. So once again, let us see what is LCM. The product of greatest power of each prime factor of the numbers. See here, to remember this easily, let us go for one small technique. We need to find LCM. L refers to least or lowest. Okay, so lowest opposite is greatest. So here it will be greatest, just like the previous one. In HCF, H refers to highest, opposite smallest, isn't it? And here L refers to lowest and opposite is greatest. Okay, and in this way we can find the HCF and LCM of given numbers using prime factorization method. Now let us try to find the LCM and HCF of some integers, and the problem given in exercise 1.2, second one. The first one has got the numbers 12, 15 and 21. So what's our first work? We need to split these numbers into the product of prime numbers. So let's start with 12. So 12 can be written as 2 6s are 12, 2 3s are 6, 3 is a prime number, we'll stop. And then 15, 3 5s are 15. So, and then 21, 21 can be written as 3 7s are 21, right there. So 12 is equal to 2 into 2 is nothing but 2 square into 3 power 1. Next 15 is written as 3 into 5. Okay, that means 3 power 1 into 5 power 1. Next 21 is equal to 3 into 7, that means 3 power 1 into 7 power 1. Now the first one, the first part of the solution is to find the prime factorization. Yes, we got that. And now we need to find LCM and then HCF. So let's start with the LCM. LCM of 12, 15 and 21 is equal to, how to find LCM? LCM is the product of greatest powers of each prime factors of the numbers. So we need to find the greatest powers of each prime factors. What are the prime factors we got? 2, 3, 5 and 7, right? Now greatest powers among those prime factors we have to see. So in 2, the greatest power is 2 square. Okay, into among 3, 3 power 1, 3 power 1, 3 power 1. All are same, so the greatest power is 3 power 1 only. Next, 5. Only one factor is there, that is 5 power 1. Since only one prime factor 5 is there, so the greatest one is 5 power 1 itself. Into 7 is also the only prime factor, and the greatest one is 7 power 1. Right. So what we are doing, LCM is the product of greatest powers of each prime factor. So the greatest powers is 2 square, and among 3 power 1 3 power 1, and 5 power 1, and 7 power 1. And now let's see, let's find the product. 2 square is 4 into 3 into 5 into 7. So let's see here, 4 3s are 12, 12 5s are 60, 67s are 420. So 420 is the LCM of the given numbers. Okay, now let's go for the HCF of the given numbers 12, 15 and 21. How to find the HCF? HCF is the product of lowest powers of each common prime factors. So here we have to see the product of lowest powers and of the common prime factors, only the common ones. Let's see here. What are common? 2 square. Is there any common? See, no. So it is the only prime factor. We don't take 2 square. Since 2 square, 2 is the only prime factor of 12, not the 15 and 21. So we are not taking 2. And 3 is the common prime factor. 5 is not having any common prime factor, and 7 also not. So only the common prime factor is 3. And among these common prime factors, 3, 3, 3, 3 power 1, 3 power 1, 3 power 1, then the lowest one is 3 power 1 itself. So when it is same in all the 3 power 1, 3 power 1 and 3 power 1, highest is 3 power 1 and lowest is also 3 power 1. So let me take the lowest one is 3 power 1 is nothing but 3. So LCM is 420 and HCF is 3. So the second question is like this: 17, 23, 29. We need to find HCF and LCM. But before finding that, let us check these numbers. 17 is a prime number, 23 is also a prime number, and 29 too a prime number. That means all these three are prime numbers. Then how to find the LCM? If all are prime numbers, the LCM of prime numbers is nothing but the product of those numbers. And the HCF of prime numbers is always 1, because the 1 is the only common factor. So automatically it becomes the highest common factor. LCM of 17, 23 and 29. Since all these are prime numbers, the LCM is product of the same numbers. Alright. So multiply these numbers, 17 into 23, and that is into 29. Then the product will be 11,339. Okay. Next, we have to find HCF of 17, 23 and 29. Since these numbers are prime numbers, the highest common factor and of these numbers will be 1, because 1 is the only common factor for any two prime numbers. So integers given in the third problem is like this: 8, 9 and 25. So let us find the prime factors for these numbers first, and then we'll find LCM and HCF. For 8 is like this: 2 4s are 8 and 2 2s are 4. So 8 can be written as 2 into 2 into 2. That means 2 power 3, right? And then 9 is equal to 9 can be written as 3 into 3. That means 3 square, right? 25 is written as 5 square, isn't it? 5 into 5. Now there is no common prime factor for these three numbers, right? Then how are we going to find LCM? Let's see here. LCM of 8, 9, 25. So once again we'll recall how to find LCM. LCM is the product of greatest powers of each prime factor of the numbers. So we have to take each prime factors, 2, 3, 5, all we have to take, and the greatest powers. Since only 1, 2 is there, and 1, 3 is there, 1, 5 is there, so whatever powers they got, they are greatest. So 2 power 3 into 3 square into 5 square. 2 power 3 is 8, 3 square is 9, 5 square is 25. Again the same numbers. Now, why? Because all these three are co-primes. They got no common factor, right? Now, 8 9s are 72, and 72 into 25. Let me find here. 25 2s are 50, and 25 7s are 175 plus 5 180. So the LCM is 1800. And what is HCF? HCF of 8, 9 and 25. What is HCF? Is the product of lowest powers of each common prime factors. We have to see common prime factors only. Is there any common prime factor? No. Since there is no common prime factor, the HCF is 1. So remember this one. If the given integers got no common prime factor, then the HCF will be 1. The fourth question has got these numbers, 72 and 108. So let me find the prime factors for 72 first. 2 3s are 6 and 2 6s are 12. 2 18s are 36. 2 9s are 18. And then 3 3s are. So 72 can be written as 2 into 2 into 2. That means 2 cube into 3 into 3. 3 square. Great. Now 108. So let's find the prime factors for 108. 2 5s are 10. 2 4s are 8. And now 2 2s are 4. 1 left. 14. 2 7s are 14. And then this can be written as 3 9s are 27. And 3 3s are 9. Okay. Now 108 can be written as 2 into 2 is 2 square into 3 into 3 into 3. 3 cube. Okay. Now 2 and 3 are the common prime factors. First we need to find LCM. So LCM of 72 and 108 is, once again, what is LCM? LCM is the product of greatest powers of each prime factor of the numbers. So each prime factor's greatest power. So what is the greatest power among 2 cube and 2 square? Obviously 2 cube into. What is the greatest power among 3 square and 3 cube? 3 cube is the greatest one. Now 2 cube answer is 2 2s are 4, 4 2s are 8. 3 cube answer is 3 3s are 9, 9 3s are 27. Now 27 8s are how much? 27 8s are 216. That is LCM. Next, HCF of 72 and 108. What is HCF? HCF is the product of lowest powers of each common prime factor. Common prime factors, 2 cube, 2 square. So lowest is 2 square. 3 square, 3 cube. Common prime factor 3 and the lowest one is 3 square. Now 2 square is 4, 3 square is 9 and 4 9s are 36 is the HCF. When you are taking, once again, remember one thing, in finding HCF, you have to compare the common prime factors. In finding LCM, you have to take each prime factor. Okay. Now, we'll move to the third question in this exercise. And it is like this. Check whether 6 to the power n can end with the digit 0, for any natural number n. If 6 power n needs to end with the digit 0, its prime factorization must contain the prime numbers 2 and 5. Let us check whether 6 power n's prime factors contain 2 and 5 or not. If it contains 2 and 5 both, then it ends with 0. If it doesn't contain, then it will not end with 0. 6 power n's prime factorization. So 6 power n can be written as 2 into 3. The prime factorization for 6 is 2 into 3. 2 3s are 6 power n. Now the prime factorization contains 2 and 3. Is this having the prime number 5? No, it is having 2 but not 5. So will it end with the digit 0 for any natural number n? No, it will not. So same thing, let me write here. Since the prime factorization do not contain 5, 6 power n does not end with 0. Fourth question is like this. Explain why 7 into 11 into 13 plus 13 and 7 into 6 into 5 into 4 into 3 into 2 into 1 plus 5 are composite numbers. So how can we find whether they are composite or not? Simple. Composite, the very meaning of composite is that it can be expressed as the product of prime factors, right? So if they can be expressed as product of prime factors, then they are composite. If they are not composite. Let's check. The first one is 7 into 11 into 13 plus 13. Now this can be expressed as, see here this expression has got two terms. The first one is 7 into 11 into 13 separated by plus, and the second term is 13. In both these terms, what is the common number present? Yes, 13 is the common number. So let me take 13 as common. If 13 is common, what is left here? 7 into 11 in the first term, 13 is common, plus 13 is common. So 13 ones are 13. Isn't it? Now 13 into 7 into 11 is 77. 77 plus 1 is 78. Now this 78 can be expressed as 2 3s are 6, 1 left, 2 9s are 18, 3 1s are 3, and 3 3s are 9. So it can be expressed as 13 into 2 into 3 into 13. That means 2 into 3 into 13 square. So now this number is expressed as the product of prime factors. That means it is a composite number. So same thing, let me write here. Since the given expression is expressed as product of prime factors, it is a composite number. Okay, And let's go for the second one. 7 into 6 into 5 into 4 into 3 into 2 into 1 plus 5, right? Which is equal to, in both the terms, here also we got two terms. In both the terms, 5 is common. So let me take 5 common. So 7 into 6, 5 is common, into 4 into 3 into 2 into 1 plus 5 is common. 5 ones are 5. Alright, 5 is common there. Product of these numbers is 1008 plus 1 into 5. 1008 plus 1 is 1009 into 5. And see here, now 1009 is a prime number into 5. So this whole expression is expressed as the product of prime numbers 1009 and 5. Okay, that means the given expression is a composite number. So same thing, let me write here, since the given expression, a given number can be expressed as the product of prime factors. What are prime factors here? 1009 and 5. It is composite. The fifth question is like this. How will you show that 17 into 11 into 2 plus 17 into 11 into 5 is a composite number? So how are we going to show that? If it is composite number, then it must be expressed as the product of prime factors. Let us check whether the given number can be expressed as the product of prime factors or not. Let's see. 17 into 11 into 2 plus 17 into 11 into 5. Now, here it has got two terms. In both the terms, what are common? 17 into 11, 17 into 11. Let me take the out. 17 into 11 is common. So what left here? 17 into 11 common, 2 plus 17 into 11 is common, 5. Now 17 into 11 into 2 plus 5 is 7. 17 is a prime number, 11 is a prime number, 7 is also a prime number. Now it is the product of prime factors. That means the given number is a composite number. So let's write the reason here. Since it is expressed as the product of prime factors. What are prime factors? 17, 11, 7. It is a composite number. So like this, well shown. The sixth question is, what is the last digit of 6 to the power of 100? So children, 6 to the power of 100, what is the value of it? Pretty difficult. 6 into 6 into 6 into 6, like this 100 times we have to multiply. But don't worry, we are not going to multiply and get the product of that. Simply we can find what will be the last digit of this given number. Let's see. 6 power 100. Let me find the prime factors of the base 6. So 6 is expressed as product of 2 and 3. 2 3s are 6 to the power of 100. Now, what are the prime numbers we got? 2 and 3. So, since this is having the prime numbers 2 and 3, the product of 2 and 3 is 6. So, it ends with 6. So, let me write the same thing. The last digit of 6 to the power of 100 is 2 into 3, the product of the prime numbers, 6. So the last digit of this given expression is 6. So this is it for this session, and in the coming video we are going to discuss about irrational numbers. And till then, practice mathematics and be happy.